Hey everyone, I thought we could look at the homework from section 3.4 on pages 136 through 139 now, since I won't be around in class to answer your questions live. I thought I'd just do the homework with you. So we're starting on page 136 and we're looking at number 16. A bullet fired straight up from the moon's surface will reach a height of s. This is my position function. S of t equals 832 t minus 2.6 t squared after t seconds. And this is feet. On Earth, with the absence of air, which I hope we never have, the height would be s of t equals 832t minus 16t squared feet after t seconds. How long will it take the bullet to get back down to the ground in each case? Well, we learned in pre-cal that we could graph these parabolas and find back on the ground by finding x-intercepts. So I just need to plug zeros in for each of these. There's no calculus I need for this. I just need to plug my zeros in. So I'm going to let you set these equal to 0 and solve for t. You can do factoring, you can do quadratic formula, you could graph these and do second calculate 0. Remember, we know there's going to be a 0 at 0 because you could factor a t out of both of these. We're looking for back on the ground in each case. Okay. All right. Why did I assign that if there was no calculus in it? Well, I think you should all think of going to the moon. And you'll want to know how things behave differently when you get there. Silly you. Okay, so this problem has not only a lot of words, but it also has this picture. When a model rocket is launched, the propellant burns for a few seconds, accelerating the rocket upward. After burnout, the rocket coasts upwards for a while and then begins to fall. A small explosive charge pops out a parachute shortly after the rocket starts downward. The parachute slows the rocket and keeps it from breaking when it lands. This graph shows velocity data from the flight. This is not position graph. This is not position graph. If this were position graph, the rocket would hit the ground and then burrow through the ground and then start climbing back out again. This is not a position graph. This is a velocity graph. Okay, so we're told here to use the graph in number 18 to answer the questions. How fast is the rocket climbing when the engine stopped? Well, that means we figured out when the engine stopped. Let's see what it said here. The rocket is launched, the propellant burns for a few seconds, accelerating the rocket upward, and after burnout, the rocket still goes upward for a little while before it begins to fall. So when the rocket is falling, velocity is negative. When velocity is positive, the rocket is rising. So I know that the rocket is rising, stops rising here and starts falling. So this is the moment when the rocket engine cut out, and then the rocket is just coasting upwards, slowing down because of gravity's effect on the rocket. How fast is the rocket climbing when the engine stopped? I think the engine stopped after 2 seconds. And I think this is my rocket speed, which is 190 feet per second. So I've got 190 feet per second. Okay, what's next? How many seconds did the engine burn? Well, the engine burned until this point, and so that was 2 seconds. When did the rocket reach its highest point? Not here. This isn't a position graph, but instead here, because this is a velocity graph. Velocity was 0. When velocity is 0 and I'm positive on one side and negative on the other, I know I've got my maximum velocity. What was the velocity then? 0. So after 8 seconds, we're at our maximum. So B was the engine burned for 2 seconds. C was after 8 seconds, we're at our max. And our velocity then is 0 feet per second. Okay, what about D? When did the parachute pop out? How fast was the rocket falling then? So the rocket starts falling and falling and falling faster and faster and faster, but they don't want the rocket to break on landing. So at this moment in time, which looks about 11, maybe 11-ish seconds, the parachute pops out. And the rocket still is falling, right? We're falling because we have a negative velocity, but we're falling much more slowly than we were here before the parachute popped out. So I think the answer to when did the parachute pop out is 10-ish, I'm sorry, 11-ish seconds. And how fast was the rocket falling then? That would be negative 90 feet per second. D, 11-ish seconds and 90 feet per second falling. Hey, don't say falling at negative 90, because falling at negative 90 means you're going up. We're falling at 90, or the height is changing by negative 90. But don't use both of those negatives, both the language one and the sign one. Use one or the other. Okay, E. How long did the rocket fall before the parachute? Wait, I thought we just did that one. What was D? When did the parachute? Oh, no, wait. How long did the rocket fall before the parachute opened? So the rocket reached its maximum height at 8, and the parachute opened up around 11. So I'm going to say that the rocket fell for 3 seconds. E, 3 seconds. And then F, when was the rocket's acceleration greatest? When was acceleration constant? All right, so acceleration is the rate of change in velocity with respect to time. That means acceleration is represented as slopes on this velocity graph. When they ask when the acceleration was greatest, they're really asking when the slopes are greatest on this graph. Well, this is negative slope. So I see lots of positive slopey stuff. I'm going to look at those instead. So this is right out. And the steepest we have over here appears to be here at this moment, just before 2 seconds. We have very steeply positive. And over here, just around 11-ish seconds, we have very steeply positive. Which one looks steeper to you? Well, to me, this rocket acceleration seems steeper than the change in velocity when the parachute pops out. So I'm going to say the steepest is just before 2 seconds. Remember, at 2 seconds, we've got a pointy point. The limit of the slopes wouldn't be the same from both sides, so we can't determine a slope at that point, too. Right? All we can do is approximate at that point. We could certainly use a one-sided derivative and say, as t approaches 2 from the negative, that's where slope is greatest. But I'm going to say instead, for F, just before 2 seconds, when the rocket burns out. That's when this thing is accelerating or thrusting fastest. Okay? Fabulous. And then the last part they said, when is the acceleration constant? Well, I think the acceleration is constant due to gravity when this is falling before the parachute stops the fall. So all this from 2 to 11 would be my answer to when is acceleration constant. Okay, so that's the first couple of questions. Let's take a look now at number 23. 23 says, the position of the body at time t is given by s of t equals t to the third minus 6t squared plus 9t. And these are in meters, so I'm plugging in a time in seconds. These are in seconds. And the question says, and this is a great test question, by the way, find the body's acceleration each time velocity is 0, which means I need to find the velocity function. Well, we know that velocity is the derivative or slopes of position. So I need to take the derivative of this. And I'm going to use my polynomial shortcuts. I'll bring down the 3, and I'll subtract 1. I'll bring down the 2 and multiply it by the 6, and subtract 1. And the derivative of 9t is 9. So I'm looking for acceleration when velocity equals 0. Okay, so I've got to find when velocity equals 0. That means I have to find when this equals 0. So 0 equals 3. Hey, I could pull a 3 out of each of those. T squared minus 4t plus 3. And this factors as t minus 3, t minus 1. And so we're looking at t equals 1 and t equals 3. These are times when velocity equals 0. But we want to know acceleration. Well, remember, acceleration is represented by the derivative of velocity, or even the second derivative of position. So let's take the derivative of this velocity graph. We'll bring down the 2. 2 times 3 will be 6. And we'll subtract 1, and we'll get t. And the derivative of negative 12t is negative 12. So if I want to know acceleration at time equal to 1, that's 6 times 1 minus 12, or negative 6. And if I want to know acceleration at time equal to 3, that's going to be 6 times 3 minus 12, or negative 6, or positive 6. So those are going to be my accelerations. But remember, these are accelerations, so we really need to put some units, especially since they told me meters and seconds. So if velocity is represented by the slopes of position, we know the change in outputs over the change in inputs. These are meters per second. So what about acceleration? Well, acceleration is a change in velocity, a slope in velocity. So we've got meters per second on top with respect to time, seconds on the bottom. So I think the answers are negative 6 meters per second for time equal to 1, and a of 3 equals 6 meters per second. And yes, you're welcome to write this as meters per second squared. However, when I look at this, and I'm not you, but when I look at this, I have no clue what the hell seconds squareds are. I do know over here that when I see these units, I say, oh, meters per second, well, that's a velocity over time. Oh, I must be talking about acceleration. So I lose the fact that these are meters per second units up top when I do this tidy, nifty shortcut notation. Okay, so that was 23. What about 24? 24. The body's velocity is given by v equals 2t to the third minus 9t squared plus 12t minus 5. And then they say find the body's speed, not velocity, speed, each time acceleration is equal to 0. Well, we know that a of t is the prime of t, and so we want to take the derivative of this. We'll bring down the 3, and then we'll subtract 1. We'll bring down the 2, and subtract 1. and the derivative of 12t is 12. I want to know when acceleration equals 0, and so t squared minus 3t plus 2, I get t minus 2, t minus 1, times 6. Set each factor equal to 0. That's never true. So this 6 is just a stretching factor. It doesn't affect where our intercepts are. T minus 2 equals 0, so we know t equals 2. T minus 1 equals 0, so t equals 1. At these places, acceleration will equal 0. And we want to know the speed at those times. Okay, so let's plug these values into velocity. I know we're not looking for velocity at time 1 and time 2. We're looking for speed, but remember, speed is the absolute value of velocity. So v of 1 will be 2, 1 to the third minus 9 times 1 plus 12 times 1 minus 5. And I get 2 minus 9 is negative 7. Negative 7 plus 12 is 5 minus 5 is 0. And v of 2, well, that's going to be 2 to the third minus 9 times 2 plus 12 times 2 minus 5. And I'm really feeling a little lazy today, so I'm not actually going to evaluate this way. I'm going to use synthetic substitution. 2 minus 9, 12, negative 5. So I get 4, negative 5, negative 10, 2, 4, negative 1. And so I get negative 1. I so prefer using synthetic substitution when I'm going to have to start cubing things and squaring things. Wait, I left out that square. There we go. Okay, so we've got 24. Oh wait, do we? No, these are the velocities. I don't want velocities, I want speeds. Speed at 1 is 0 meters per second. These were in meters per second, weren't they? Yes. And speed at t equals 2 seconds is 1 meter per second. Right? It's got to be positive, not negative. Velocity was negative, but speed is always positive. Okay, 25. It takes 12 hours to drain the storage tank by opening a valve at the bottom. The depth y of fluid in the tank after t hours. So y is how deep the fluid is, and t is time in hours squared, and the depth is measured in meters and time is measured in hours. Find the rate dy dt at which the water level is changing. Okay, so they're asking us to find the derivative of this. But I've got stuff in here. This isn't the same as 6t squared. If I had 6t squared, 12t would be my derivative. Well, it turns out that we can't do that here. We're going to have to rewrite this. It's 1 minus t over 12, 1 minus t over 12. And so then I'm going to have to FOIL. I'm going to have y equals 6. 1 minus this times this times this times 2 would be t over 6. And then I've got plus t squared over 144. I can distribute that 6 now, and I get y equals 6 minus t plus 144 divided by 6. I think it's 24. Let's see. 144 divided by 6. Yes, it is 24. Okay. So plus t squared over 24. So here's my y function. Therefore, y prime, or dy dt, the derivative of this function with respect to time. The derivative of a constant is 0. The derivative of negative t is negative 1. And the derivative here, well, it would be good if you thought of this as t squared times 1 over 24 and didn't think, I should use the quotient rule here. Because it's much easier to do this problem as the derivative of a constant times t squared. You bring down that 2, so you've got 2 over 24, which is 1 over 12t. Okay, so there's my derivative. Oh, by the way, those of you who like quotient rule and want to use it here, you can. It's just going to be a lot more time consuming, and you might make mistakes with low d high minus high d level over low squared. Okay, so there's part A. Part B. When is the fluid level in the tank falling fastest? When is the fluid level in the tank falling fastest? Well, let's think about this. I've got here a linear function. It's got a negative y-intercept, or yes, negative y-intercept. And so if I make a little graph of this, I have dy dt over here, I have t over here, and my graph looks like this until I get to 12. Oh, no, that's not where 12 is it? No. If I put a 0 here and add 1 and multiply both sides by 12, I'll find out that this is 12. And this is 0, negative 1. Okay. So this is my dy dt graph. This is the rate at which the level of fluid is changing in the tank. At time equal to 0, the rate is most negative. I'm falling fastest at negative 1 meter per second. At time equal to 12, that rate of change is now 0. And that makes sense to me because after 12 hours, the tank is empty. There's no more fluid, they told us, to empty out of it. So this is when the tank is emptying slowest because it's not emptying at all. And this is when the tank is emptying fastest here at time equal to 0 at a rate of negative 1 meter per second. Okay, what are the values of dy dt at these times? At time equal to 0, falling fastest at negative 1 meter per second. At time equal to 12, falling slowest at 0 meters per second. It says graph y and dy dt together and discuss the behavior in relationship to the signs and values of dy dt. All right, well, let's think about that. And our original function was a parabola shifted over and so here's my parabola graph, and what we see here is the level is decreasing, 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 decreasing until at time equal to 12, the level, this is y. Why don't we do this in a different color? That's what different colors are made for. Parabola. So here's my y, and here's my dy dt. Okay. So notice the most negative slope is here at time equal to 0. These are still negative slopes. They're heading towards a 0 slope as the tank empty after 12 hours. I know that y is positive because there's still fluid in the tank. But y's values are getting smaller and smaller and smaller, heading to 0 as the tank empties out. I see y prime is negative because that's the rate at which the tank is emptying. If the rate were positive, the tank would be filling up. Since these rates are all negative values on the blue graph, that tells me that all the rates are negative, and therefore the tank is emptying from 0 to 12. That's a great test question. Okay, next we've got, it looks like 31. And 31 is something we've had a little practice with. We're asked to figure out which of these functions is whose derivative. And they've told us that one of the functions is position, one is velocity, the derivative of position, and one is acceleration, the derivative of velocity or the second derivative of position. So what I do is what we did in class. I start with the zero slopes. And I'm going to start with graph C because it has the most maxes and mins. And I see, oh look, a zero slope. Oh look, a zero slope. And notice down here, a 0. And notice here, a 0 on the A graph. So I think A represents the derivative of C. Let's just confirm that. From this point to this point, slopes are negative. From that point to that point, the derivative would be negative. Oh, good. So A is the derivative of C. Now, where does B fit in? Well, if I repeat that process with A, I have a 0 slope here, and I have a 0 on B here. I have negative slopes on A up to this point, and so the derivative is negative up to that point. I have positive slopes after that point, and the derivative positive slopes after that point. So I think C is the original function, A is the derivative of that function, the first derivative, and B is the derivative of A, or the second derivative of C. Okay, let me write that down. We've got F equals C, we've got F prime equals A, and we've got F double prime or A prime equals B. I guess this could also be called C prime. Cool, so that was number 31. What about 32? 32 is similar, but in this one, many students tell me, well, Mr. Kukla, I did it because I was thinking about this being a third-degree polynomial, and the derivative would be a second-degree polynomial, and the derivative of that would be a first-degree polynomial. That's a little harder to do when we look at, I can't quite get to that picture. Oh no, I better draw it off to the side here. Okay. So I've got a graph, and I've got a function. That's A, and I've got B, and I've got C. Okay, so here's what I think I see. I see some zeros on B, and on C, this kind of looks like a 0 slope, and this kind of looks like a 0 slope. So I think B is going to be the derivative of C. Let's just check. The slopes on C. What do we notice about the slopes here? Well, C is decreasing, 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 decreasing. So the slopes on C are always negative. And lo and behold, the derivative here is always negative. I have a 0 slope, I have a 0 slope, I have these zeros. So I think that B equals C prime. Now, where does A fall into this? Is A the derivative of B, or is C the derivative of A? Well, let's see what we've got. Here, it kind of looks like I have a 0 slope. Okay. But I don't have a 0 here, so either that's not a 0 slope, or it is, and yeah. All right, well, what do we see about the slopes here? The slopes here are all positive slopes. So I would expect the derivative of A to always be above the x-axis. I don't see anything above the x-axis except A. So A is not my original function, because A's derivative would have to be B or C, and neither B nor C is above the x-axis. So A can't be my first function. I think A is supposed to be the derivative of B. Let's confirm that. At here, I have a 0 slope, so I have a 0. Oh, nice. Here, I have negative slopes on B, so I have negative y values on the derivative graph. Here I have positive slopes, not y values. Here I have positive slopes on b, and therefore a, the derivative, is positive. So I think that a equals b prime or c double prime. Okay? Pay attention to the difference between whether we're talking about the y values on a function or the slopes on a function. Here, all the y values are negative and all the slopes are negative. But here, all the y values are negative, but the slopes are negative, and then the slopes are positive. Here, the y values are negative, but the slopes are positive. And here, the y values are positive, and the slopes are positive. So we want to pay attention to all those details when we're doing this. Okay, number 37. Let's take a look at you. Particle motion. We've got the line we're moving around. I'm sorry, this is just the funniest thing. The position of a particle moving on the line y equals 2 is given by x of t. Remember, this is a variation of s of t for position equals 2t to the third minus 13t squared plus 22t minus 5. Now, why did I laugh so much? Because I think it's the funniest thing that there's this y equals 2 line, and there's this little particle moving back and forth along that line, and this function represents the position at any moment in time t along that line of this particle. And then I got to say to myself, there's a particle moving. Who the hell cares about a particle? But it turns out, in a lot of physics, we really do care about the position of particles, even when they're moving on a straight track back and forth. So, yeah, actually, even though it sounds kind of funny to be wondering about a particle moving along this straight line, hey, and notice, moving along this straight line, it's not this graph. This is not the position graph, right? We're not looking at this position graph. We're looking at back and forth along y equals 2. So when we're thinking about this, we're thinking moving to the left, stops, moves to the right, stops, moves to the left, stops, moves to the right. But we're going to experience that in this problem as moves to the left, stops, moves to the right, stops, moves to the left. Oh, okay. Well, let's see what they're asking us to do in this problem in the first place. Describe the motion of the particle for time t greater than 0. Okay, well, so I know that this is x of t, v of t would be the derivative of this, 6t squared minus 26t plus 22. And when I think about the velocity graph, I see that velocity has an intercept at 22. When I graphed on my calculator, I had 1.5, I had 3.18, and here I had 2.17. You should really take these to 3 decimal places. I'm sorry I don't have those for you right now. So what can we say? Well, I see velocity is positive, so the object is moving to the right until this moment in time. Then the velocities are negative. I reach my maximum negative velocity at time 2.17, and then we start slowing down again. We're still moving to the left. At time 3.18, we stop moving to the left and we start moving to the right again. Let's look at our position function for a moment, our x of t. Our x of t is this polynomial function, and I've got, what do I have? I've got zeros at, do I have zeros at? Time equal to 0, x is negative 5. Okay, so if I plug a 0 in here, I get negative 5. I know the initial position is 5 to the left of something. Okay, and then here, this is at time equal to 1. And here, we've got time equal to 3. But we know it's really 1.5 and 3.18 because these zero slopes turn into zeros on the velocity graph. Okay, and what can we say here? At 3, if I plug a 3 into position, I get -2. So I'm not as far to the left as I was x of 3 equals -2, as I was before. So let's talk about what's happening with this particle. Okay, particle is moving to the right and stops. So the particle is moving to the right. It passes the origin, continues to move to the right because of these positive slopes, goes as far as possible to the right as it's going to go initially, and then it stops moving at this 1.5 second moment. We start moving to the left because of these negative slopes. We reach our maximum to the left at 2.17. And then we start heading back to the right. Oh no, I'm sorry. We're still moving to the left, right? All these negative slopes, we're moving left, we're moving left, we're moving left. Okay? And then we start moving to the right again because velocity is positive and because slopes are positive. So we're moving to the right, moving to the right, moving to the right. What's this line? This is the origin. Imagine that our particle is moving along the axis, along this line back and forth, and at this arbitrary place called x equals 0, that's where these points are. And so this point, -5, is over here, and this point is over here. In positive land, we start moving negative, 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 so we're back here at -2, and then we start moving positive again, so we're going to go back over here. Okay, so that was a lot of talking. When does the particle speed up? When does the particle slow down? Well, I know that the particle is going to be speeding up from, here we go, 1.153. I need a new pen. 1.153 to 2.167. And I know the particle is going to be speeding up from 3.180 forever because this thing doesn't stop. Okay, so speed up 1.153 to 2.167 and union 3.180 to infinity. This is speeding up. So slowing down, we've got 0 to, and I guess you could use a bracket here, 1.153 union 2.167 to 3.180. Okay, so then the question is, Mr. Kukla, how'd you know that? Well, I graphed the speed graph. Remember, speed is the absolute value of velocity, so I'm going to make the absolute value of this velocity graph. All these negative velocities have to flip up. So, what can we say about speeding up? I say we're speeding up from here to here because of the positive slopes on the speed graph. And I say we're speeding up from here to infinity, or from here to infinity, because, again, slopes on speed are positive. I think we're slowing down from 0 to here, 1.153, because the slopes here are negative on the speed graph. And from 2.167 to 3.180, I think the speed is, that we're slowing down because the slopes here are negative as well. So take a look at that speed graph. Okay, what's next? That was B. When does the particle change direction? Well, the particle changes direction here and here on the position graph, or on the velocity graph here and here. When velocity goes from positive to negative, when velocity goes from negative to positive, that's when I'm going from left to right or from right to left. I think I said that right. Here, positive velocity, moving to the right, stops moving, starts moving to the left. Positive velocity, moving to the right because of these slopes. Look, my position was -5, and now I'm way up here. So I must have moved to the right, moved to the right, moved to the right. Then I'm moving to the left, moving to the left, moving to the left. So I'm moving to the right, I'm stopping, I'm moving to the left. Moving to the left a lot, I'm stopping. I'm moving to the left because of these negative. I'm moving to the left because we're below the axis. Moving to the left, moving to the left. Ah, sorry. Stop. Oh, especially Riley, I'm sorry. Look, over here on velocity, whenever velocity is negative, the object is moving to the left. But over here, it's the negative slopes from here to here. I'm moving to the left, moving to the left, moving to the left. So negative slopes on position, negative y values on velocity. These negative slopes tell me I'm moving to the left. These negative y values tell me I'm moving to the left. And then I'm moving to the right because of these positive slopes, and I'm moving to the right because of these positive y values. Woof! So the particle changes direction at 1.153 and 3.180, and I can see that on either of these graphs. When is the particle at rest? When the slopes are 0, when velocity is 0. So at 1.153 and 3.180. Describe the velocity and speed of the particle. I've done that already. When is the particle at the point 5,2? When is the particle at the point 5,2? Did I ask you that one? Oh, no, I didn't, so I'm not going to worry about that. Okay, last 3 questions. Let's take a look at those. We've got number 43. Find the instantaneous rate of change in the volume of a cube with respect to its side length. Volume of a cube with respect to its side length, and we're told that the side length must be x. So volume is x to the third. They'd like to know the derivative of volume, derivative with respect to x of volume, which will be the derivative with respect to x to the third. Okay, so let's take the derivative of that, and we'll say that dv dx equals 3x squared. And that corresponds to choice D. Okay, so there's 43. What about 44? 44 says particle moves along where position is given by 2 plus 7t minus t squared. 4t greater than or equal to 0. At which of the following times is the particle moving left? Well, I just found it in that problem a few minutes ago much easier to figure out the particle is moving left when the velocity was negative. So I'm going to take a look at velocity. V of t is 7 minus 2t. And I'm going to look at this graph, which has positive y-intercept and a negative slope, 3.5. And are we going forever? At which of the following times is the particle moving left? Okay, so this is 3.5. So if this is my velocity graph, positive velocities mean moving to the right, negative velocities mean moving to the left. So from time 3.5 on, this object is moving to the left. My choices here are time equal to 0, no, we're moving to the right. Time equal to 1, no, we're moving to the right. Time equal to 2, no, we're moving to the right. Time equals 7/2. No, we're actually stopped at that moment in time. Velocity is 0 here. Time equal to 4. E is my answer. Time equal to 4 is when I'm moving to the left. E, t equals 4. At t equals 4, I've got a negative velocity, so I'm moving to the left. And our last problem, number 45, says, when is the particle at rest? Oh, I just answered that question. It's when velocity equals 0. 7 minus 2t, so t equals 7/2, and that happens for letter C. All right, so 45 minutes to finish your homework, even at a slow, rambling pace. Have a wonderful